Hey, welcome. We're surrounded by these incredibly complex systems. Everything from the weather to our own bodies. And to understand them, we don't just sit on the sidelines and watch. We build them inside our computers. We create these amazing virtual worlds, digital copies of reality, that let us predict, innovate, and make decisions in ways we never could before. And today we're going to dive into exactly how that happens.
That's the big question, isn't it? How on earth do you predict the path of a hurricane? Or the crazy swings of the stock market? Or even figure out if a new medicine is actually going to work? These systems are just this chaotic dance of a million different moving parts, which makes their outcomes feel totally random.
And the answer is actually kind of brilliant in its simplicity. We build digital sandboxes. We create these virtual worlds where we can run thousands, even millions of experiments, safely and without spending a fortune. These simulations let us test our wildest ideas, explore all kinds of different futures, and really figure out what makes these complex systems tick. And the best part? No real-world consequences.
Okay, so to really get a handle on the kind of power we're talking about, we first need to break down what these computational models actually are and how they're put together.
The easiest way to think about it is this. A model is just a set of rules that stands in for a real-world system. So, take a weather forecast. That model is crunching countless variables, temperature, air pressure, wind speeds, and it's running them through equations based on the laws of physics to tell you if you need an umbrella tomorrow. Or think about a flight simulator, which uses the principles of aerodynamics to perfectly copy how a real plane would react if you suddenly hit a patch of turbulence.
Now, when it comes to building these digital worlds, there are really two main ways to go. On one side, you've got mechanistic models. These are built on scientific laws that we completely understand. We know why they work. But on the other side, you've got data-driven models. You can kind of think of these as the black boxes. They learn by sifting through massive amounts of data to find patterns and make predictions, even when we can't fully explain the why behind what they're doing.
And these models are getting just unbelievably detailed. We're now at a point where we can build what are called multi-scale models. So imagine not just simulating a heart, but also simulating the individual cells inside that heart, and the proteins inside those cells, and even the molecules that make up those proteins, all at the exact same time. It's this incredible depth that gives us a view of how a system works like we've never had before, from the tiniest parts all the way up to the whole thing.
So, having a brilliant idea for a model is one thing, but how does it go from being a cool concept in a research paper to a tool that we actually trust and use every day, like a flight simulator? Well, it turns out there's a pretty formal process for that.
And that journey is tracked using something called the Technology Readiness Level Scale, or TRL for short. NASA actually came up with this to make sure technology was ready for space missions, but now it's basically the gold standard for measuring how mature any new tech is. And that includes our models. It's the roadmap from idea to impact.
So the whole journey kicks off in the idea phase. This is pure research. It all starts with a basic concept, then it moves into some early experiments, and it ends with a proof of concept, usually a published paper that shows, hey, the basic science here is solid.
Next up, things start to get a lot more practical. That idea gets built into a working prototype. It gets tested first in a controlled lab setting and then in environments that are designed to mimic the real world. By the time you get through this phase, the concept is really starting to look and feel like an actual tool.
And here we are at the final stage, taking the product out into the wild. The prototype gets handed over to the first real customer for beta testing. After you take their feedback and bake it in, the model becomes a complete system, and finally, it's a proven, reliable product that's being used successfully in the real world.
But just because you've reached the end of that road, just because a model is finished, that doesn't automatically mean we can or even should trust it. Earning that trust requires a whole other process to make sure the model isn't just complete, but that it's also correct.
And this brings us to a super important distinction: verification versus validation. Verification asks the question, are we building the model right? It's kind of like proofreading the code to make sure there are no typos, and then it matches the blueprint exactly. But validation asks a much deeper, more important question. Are we building the right model? That's like fact-checking its answers against reality to make sure it's an accurate copy of the real world.
In that validation process, it follows three key steps. First, there's face validity. Do experts in the field look at it and say, yeah, that seems reasonable? Second, you have to validate the assumptions. Are the theories and the data you built it on actually correct? And finally, the ultimate test. If you give the model and the real world the exact same inputs, do you get the same outputs? All right, so once a model is verified and it's validated and we actually trust it, well, that's when its true potential gets unlocked. So let's look at just a few ways these powerful digital worlds are already shaping our physical one.
One of the most mind-blowing concepts out there today is the digital twin. Now, this isn't just a static model, it's a living, breathing, virtual copy that is constantly being updated with real-time data from a physical object. The twin literally evolves right alongside the original, creating this perfect digital mirror for testing and prediction.
To really make that concrete, just imagine this for a second. A cancer patient has a digital twin built from all of their lab tests, their medical images, everything. As their disease changes in the real world, the twin gets updated in real time. Doctors can then use this digital patient to test thousands of different drug combinations and treatment plans virtually to find the most effective, personalized strategy before ever giving a single dose to the real person. It's incredible.
And these kinds of applications are just exploding everywhere you look. In medicine, we're modeling hearts to fight disease. In finance, algorithms are optimizing multi-billion-dollar investment portfolios. During a pandemic, models track the virus to help guide public health policy. We're even building models of the brain itself to try and unlock the mysteries of how we think.
Okay, but all of this incredible power to simulate and predict, it comes with enormous responsibility. These models, they aren't neutral. They're designed by humans, and they're trained on data created by humans, and because of that, they can inherit some very, very human flaws.
And this right here, it lays out that central tension perfectly. For every single promise, there's a potential peril. That flexibility we get from remote work can turn into the techno-stress of feeling like you're always on. Health apps that help us can also create huge privacy issues. And the social connection we get from online platforms can so easily slide into echo chambers that are just filled with misinformation.
And probably one of the most critical dangers here is algorithmic bias. See, if a model is trained on biased historical data, let's say a hiring model that learned from decades of decisions from a company that mostly hired men, it's going to learn and then repeat that bias. So instead of creating a fairer world, the model can accidentally automate and even amplify past injustices, creating this vicious cycle of discrimination.
Which leaves us with this final, really crucial question. Computational models give us this unprecedented power to understand, predict, and even shape our reality. They are mirrors that reflect our world back at us, but they also have the power to change that world. So as we get better and better at building these digital copies, we have to keep asking ourselves, are we using them to build a better reality? The choice, really, is ours.